So today we're going to talk about feedback loops. We're going to cover the different types of feedbacks. We're going to practice drawing some systems diagrams, and then we're actually going to create some graphs of these interactions. So our first example is going to deal with the rabbits and the grass and the wolves simulation that you should have just finished. So we're going to try to create a system diagram of actually what's happening between the rabbits and the grass. So we're going to start with an increase in rabbit population. The rabbits had a bunch of babies, oops, that spring. And as they have more rabbits, the rabbits are going to eat more grass. The consumption of grass will increase. And as a result, there's going to be less grass available. Makes perfect sense, right? So this is an important food source for the rabbits, right? This is their limiting factor, the amount of food that they have. So since there is now less grass, the number of rabbits is actually going to go down. We have a drop in the rabbit population. You'll notice here, we started with an increase in rabbit population, and now we're ending with a drop in rabbit population. So the initial change has been reduced, or in this case, completely reversed. This is what we call a negative feedback loop. Because it's doing basically the opposite of how it starts, right? We started with an increase in rabbit population, and then something happened which made the rabbit population go back down. These are going to be stabilizing systems, which will keep things in equilibrium, right? You might have noticed that the rabbits seemed to be in equilibrium as they were existing. So negative feedback loops, these tend to be de-amplifying. That is, they decrease the initial change. Decrease the initial change. So we could continue to think about this interaction, right? If we start with a drop in rabbit population, that's actually going to be a good thing for the grass, right? Because that means there's going to be less grass eaten or less grass consumed. And as a result, there's going to be more grass available. And now we have an available food source. So as a result of that grass growing back up, we're actually going to have an increase in rabbits. Rabbit population. So again, right, looking at our initial change, we started with a decrease in rabbits, and then we ended with an increase in rabbits. So these are not the same, right? Not equal. So this would be, again, your negative feedback loop. So now we're going to try to graph this interaction. So I have my axes here with time on the x-axis, and then abundance or number of rabbits or grass listed here on the y-axis. And then I'm using green for grass and blue for rabbits. So let's walk through that first example, right? We started with an increase in rabbit population. And as a result of that increase in rabbit population, they started to eat more grass, right? So the amount of grass actually went down. And so now there's a smaller food supply with a larger population of rabbits, right? So as a result, the population of rabbits goes way down. This could be like a famine right here, might be happening. So the rabbit population plummets, right? This is our negative feedback loop. We started with an increase, now we're going to a decrease. And as the rabbit population drops, you remember, that means there's less grass getting eaten. So at this point, the grass actually starts to rebound. So the abundance of grass will start to go up. You might notice now, our rabbits have a really adequate food supply and not a lot of competition, right? There's a really few number of rabbits. Maybe this is, say 20 rabbits, and this is say 100 rabbits, just some random numbers for our ecosystem. But as they have more food, the population of rabbits will start to increase again. They're like, oh yay, we're at the salad bar, we're having a feast. But since they're eating more food, the population of grass actually will go back down as a result, and perhaps you already recognize the pattern of what is happening. This is a classic version of what you get in a negative feedback loop. This kind of oscillating pattern, which goes around some sort of stable equilibrium. You might recognize this as exactly what happens in a steady state equilibrium. All the different inputs and outputs have negative feedback loops, which keeps the system in balance, keeps it at equilibrium, keeps it stable. So my favorite example is actually body temperature. You're actually using negative feedback loops all the time without even thinking about it or trying to. So our body temperature usually should be around a stable point, but maybe you have to go to sports and you have to be out in the hot sun and you're very upset and you have to run around the soccer field and your body temperature starts to increase. And you're like, oh, this is really awful. Why are they making us do this out here? As your temperature starts to increase, your body does some things automatically, right? You start to sweat. And so that sweat actually, as it evaporates, will cool down your body temperature. So at this point, we start to sweat. And if it's happening right, the sweating should help cool your temperature and you'll return back to normal, back to equilibrium. And then maybe you finish soccer practice and you forgot to bring a coat and you're trying to walk back up after the sun has gone down and it actually starts to get really cold and maybe your body temperature actually dips below what it should be. At that point, you automatically might start just shaking and shivering, right? So that's your body's reaction to that. And as you shiver, you're actually using energy and generating more heat to return your body back to that stable equilibrium. In biology, they use words like homeostasis to refer to the kind of equilibrium state of different things. So sometimes we can have kind of the opposite happening. So let's say you're shivering and you're really cold, but instead of in Arizona, you're way up in the Arctic, right? So you're getting colder, and then you start to reach a point where you become hypothermic. Hypothermia. Hypo means too little versus hyper, which is like too much, hyper, I have lots of energy. Hypo would be the opposite. So in this case, hypo, really low thermia, temperature, low temperature. Your body is getting so cold that you're actually starting to shut down. So shivering hasn't worked at this point, and maybe you actually are going to stop shivering, which is a bad sign. You just lost that negative feedback loop. And sometimes people are actually going to start losing like their mental functions at this point. They start to be like really disoriented. They don't even know what's going on. Some people actually start feeling like they're hot and they start taking off their clothes. So they get this like sensation of being too warm. And as they take off their clothes, they end up getting even colder, right? Until eventually you get past the point where it's way too late. This is really, really severe hypothermia. Sometimes they find people totally stripped down out in the wild because we just ended up in what's kind of a snowballing situation, right? They were getting colder. They ended up where the shivering didn't work anymore. Their brains started to break down and everything just started to snowball until they ended up in a really terrible situation. A similar snowballing effect can happen when you have feedback, as I actually call it, in music or in sound recording. So this actually happened briefly during community meeting a week or two ago, where we have our usual setup, right? So when it works out fine, you have your announcer talking into the microphone, which then transmits the sound out of the speaker, right? Everything works great. You can hear them much better. What happens, what goes wrong is if this microphone goes in front of the speaker, right? So this speaker is putting out the sound. And if this microphone goes in front of it, all of a sudden this microphone is picking up the sound from the speaker. And once that microphone picks up the sound, it automatically sends it into the speaker. And so now that sound comes back out of the speaker. and then it actually goes back into the microphone, and then it goes back into the speaker, getting a little bit louder, and then it goes back into the microphone, and then back into the speaker. And at this point, it sounds like, and it like hurts everyone's ears, and it sounds really terrible, and it happens so fast because these can snowball out of control very quickly. These are our positive feedback loops, and we call them positive feedback loops, even though this is not a positive thing. I don't think I've ever met anyone that likes this sound, unless they're, you know, like a rock and roll musician. Sometimes they make feedback on purpose. But this is what's happening, right? We end up in a loop where we keep going around and everything keeps increasing. Everything keeps snowballing out of control. These are very destabilizing systems. Whoops, destabilizing. I think this might be an A actually, but that's okay, spelling doesn't count. Destabilizing systems, which actually amplify any sort of initial change. Amplify the initial change, which makes sense, right? This is actually an amp that you're using. Amp is short for amplify. So it's amplifying that initial change, and in this case, just ending up in a loop where that amplification just keeps increasing until everyone's eardrums shatter, and then you're very sad. So let's draw an example of this dealing with air conditioning and climate change. We'll abbreviate both of those, air conditioning and climate change. So it's getting a little bit warmer out there. I don't know if you guys have noticed that. We've had an increase in temperature. And personally, when it gets hot out, I like to turn up my AC. Crank up that AC, right? However, we're in Arizona. We're not the most forward-thinking state. So a lot of our electricity actually comes from fossil fuels, right? So using that AC increases my electricity use, which is actually coming from things like natural gas, increased fossil fuel use overall. And as you've heard probably since the day you were born, more fossil fuel burning creates more CO2. Everyone's favorite. And of course, because of the greenhouse effect, CO2 actually will increase the temperature since it's a greenhouse gas. And then as the temperature increases, you're going to want to turn up your AC, right? And as you turn up the AC, you use more electricity, which burns more fossil fuels, which then creates more CO2, which raises the temperature further, which makes you want to put on your AC, which uses electricity, which you can see how this snowballs very, very quickly. And then can lead to a system that's totally out of balance. Luckily, this is not the only feedback loop that happens in the climate. There's lots and lots of other feedback loops, many of them negative, many of them positive. We'll explore what some of them look like. But this is just one tiny example of a feedback loop that is occurring in the climate system, which may or may not affect everything else. Well, it will, just to what degree it does is the real question. So let's try to graph this interaction. Once again, I'm going to make a line graph here. And a line graph works really well in this case because we have time, so we have continuous change. So we can show how that changes on a continuous gradient versus specific different categories or things like that. So we're starting with an increase in temperature. It's getting a little bit warmer. We start to use our ACs, we burn fuels. And then the temperature keeps going up, and then we use more AC and we burn more fossil fuels and release more greenhouse gases. And you can see very quickly that this does not change directions. This just continues on as an exponential curve, right? Keeps going in the same direction forever. Very bad thing. You also could graph electricity use, right? Even if we're starting with low electricity, as the temperature increases, we're trying to use more AC, so our electricity use is going to go up. And then we're going to increase the temperature and then want to use more electricity. And so these things are actually going in the same direction. So they're just amplifying each other and they're just encouraging each other and not, in a negative feedback loop, things go back to normal. In this case, we are not going to equilibrium. We are going to tipping points where we go to a new equilibrium. Sometimes a new equilibrium might be a good thing. So there's lots of positive feedback loops involved in pregnancy. When you're about to give birth, you start to release oxytocin, which creates contractions. And as you contract, you release more oxytocin, which creates more contractions, which leads on and on and on and on until eventually you push the baby out, right? So you started in one equilibrium where you were pregnant, and you ended up in a new equilibrium where you weren't pregnant anymore, and you had hopefully a beautiful, healthy baby. In that case, it's a great tipping point. It's actually, the circle of life. Some tipping points are less good, as we can see with climate. But there'll be much more on tipping points to come. But for now, you're going to practice drawing some systems diagrams and graphs of different feedback interactions.